What is ISA total air temperature? Now, total air temperature is different from static air temperature. Static air temperature is the ambient temperature around you or in the atmosphere. Total air temperature is static air temperature plus plus some extra value. Okay, that extra value or plus some extra heat that is registered by the temperature probe situated or installed in your on your aircraft fuselage. Okay, so the total air temperature is nothing but indicated temperature to you in the cockpit. This indicated temperature will not be equal to static air temperature or ambient temperature outside. It will be slightly more than that because the relative airflow which comes towards the temperature probe will strike the temperature probe and there will be a rise in heat because of that impact pressure, and this extra heat gets added to static air temperature, and the final result that is shown to us on the screens is the total air temperature. So static air temperature and total air temperature are different values. Total air temperature will be slightly more than static air temperature. Now here they have asked us to find out total air temperature. If they had asked us to calculate static air temperature, we would have just applied lab state formula to 30,000 feet pressure altitude and calculated that. But for total air temperature, the formula is total air temperature equals to static air temperature, big bracket 1 plus 0.2 into recovery factor into Mach number the square. This is the big formula. Now over here, remember static air temperature and total air temperature are in Kelvin. In this formula, they are in Kelvin. Okay. So what is the pressure altitude? Pressure altitude is 30,000 feet. So at 30,000 feet, static air temperature is going to be equal to, static air temperature is going to be equal to 15 degrees Celsius minus 2 into thousands of feet. So 30,000 feet, so 2 into 30. So 15 minus 60, which is minus 45 degrees Celsius. Now minus 45 degrees Celsius is equal to minus 45 plus 273, that is 228 Kelvin. 228 Kelvin. Now let's substitute the values here. Total air temperature equals to 228 Kelvin, big bracket 1 plus 0.2 recovery factor. Now if the recovery factor is not given in the question, you consider it 1, the value 1. So into Mach number. Mach number is 0.84. So 0.84 multiplied by 0.84, 228, 1 plus 0.2 into 0.84 into 0.84, that is equal to 0.14112. So 228 times 1 plus 0.14112 is equal to 1.14112. So 228 into 1.14112, that is 260 Kelvin. So total air temperature equals to 260 Kelvin, or in terms of degree Celsius, it will be equal to 260 minus 273, approximately minus 13 degree Celsius. Minus 13 degree Celsius. So you are going to select this option or any option which is closest to this. Fine. So this is the answer to question number 1. Now question number 2. If indicated total air temperature is minus 10 degrees Celsius, pressure altitude is 30,000 feet, Mach number is 0.84, what is ISA temperature deviation or normal temperature deviation? So let's find out the original true air temperature, and then we will compare that true air temperature with indicated true air temperature to get temperature deviation. So total air temperature equals to static air temperature into 1 plus zero point 0.2 recovery factor into Mach number square. So at 30,000 feet, at 30,000 feet, static air temperature is equal to minus 45 degrees Celsius. Now minus 45 degrees Celsius is equal to 228 Kelvin, right? Is equal to 228 Kelvin. So 228 1 plus zero point 0.2 into 1 into 0.84 into 0.84. So 228 1 plus 0.84 into 0.84 into 0.2, that is equal to 1 plus 0.14112. 228 multiplied by 1.14112. So 228 into 1.14112, that is equal to 260 Kelvin. 260 Kelvin. Now 260 Kelvin equals to approximately minus 13 degree Celsius. Okay, so total air temperature is minus 13 degrees Celsius. You're getting indicated a total air temperature of minus 10 degrees Celsius. So that means temperature deviation is equal to indicated total air temperature minus real total air temperature. So indicated is minus 10 degrees Celsius minus of minus 13. So minus 10 plus 13 is 3 degrees Celsius. That means the indicated temperature is 3 degrees Celsius warmer than real total air temperature. Next, the pressure altitude is 40,000 feet. Indicated total air temperature is minus 29 Celsius. What is the Mach number assuming ISA conditions? Okay, so in ISA conditions, static air temperature above 36,090 feet is equal to a constant value of minus 56.5 degrees Celsius. So 40,000 feet is above 36,000. Therefore, static air temperature at 40,000 feet will be equal to the same temperature, that is minus 56.5 degrees Celsius. Now that is equal to minus 56.5 plus 273, 216.5. So consider 216 Kelvin. Fine. So now let's use the formula. Total air temperature is equal to static air temperature 1 plus zero point 0.2 recovery Mach number square. So static air temperature 216, 1 plus zero point 0.2 into recovery into Mach number square. Total air temperature is minus 29. So minus 29 is plus 273 is 244 Kelvin. So 244 equals to 216 recovery factor 1 0.2 into 1 into m square. So 244 divided by 216 equals to 1 plus zero point 0.2 into Mach square. So 244 divided by 216 is 1.129er. So let's consider 1.13, which is equal to 1 plus 0.2 into Mach square. So 1.13 minus 1 equals to zero point 0.2 into Mach square. So 1.313 minus 1 is 0.13 divided by 0.2 equals to Mach square. So that is again divided by 0.13 divided by 0.2 is 0.65. So Mach number will be equal to square root of 0.65 is 0.8. Okay, so Mach number is 0.806, 0.81, whatever. So Mach number, what is the Mach number? So the Mach number is 0.8, 0.81. Okay, some value close near that number. So this is how you do the sum. Be careful while doing the calculation. Next, if Mach number is 0.88, total air temperature is minus 4 Celsius. What is the pressure altitude in the ISA? Okay, so let's find out the static air temperature. In order to find out pressure altitude, we must know static air temperature. And then we will relate or associate that static air temperature with a particular pressure altitude found in the ISA. So total air temperature equals to static air temperature 1 plus zero point 0.2 into recovery factor into Mach square. Okay. Now total air temperature is minus 4 degrees Celsius. So minus 4 plus 273 is 269 Kelvin. 0.2 into 1 into 0.88 into 0.88. So 269 equals to static air temperature 1 plus 0.2 into 0.88 into 0.88, that is 0.15488. So 269 equals to static air temperature times 1.15488. So static air temperature equals to 269 divided by 1.15488. That is equal to 232.9 or 233 Kelvin. The static air temperature is 33 Kelvin, that is equal to minus 40 degree Celsius, right? So minus 40 degrees Celsius. Now we have to find out at what altitude in the ISA atmosphere do we get or do we tend to find minus 40 Celsius. So minus 40 degrees Celsius equals to 15 degrees Celsius minus 2 into pressure altitude. So minus 40 minus 15 equals to minus 2x. So minus minus plus minus 55 equals to minus 2x. So x equals to 55 divided by 2, that is 27.5 or 27,500 feet. So at this altitude you are going to find minus 40 degrees Celsius. That means aircraft is flying at a pressure altitude of 28,000 feet. It would be safe to say aircraft will be flying at or is flying at 28,000 feet. If pressure altitude is 30,000 feet, total air temperature is -10, Mach number is 0.82. What is the density altitude? Okay, what is the density altitude? So, total air temperature equals to static air temperature, right? 1 plus zero point 0.2 into recovery factor into Mach square. So this is your indicated total air temperature, -10. So let's write that down. 1 plus zero point 0.2 into recovery factor into Mach number 0.82. So -10 degrees Celsius plus 273, because we want a final answer in Kelvin, is equal to 1 plus 0.2 into 0.82 into 0.82, that is equal to 0.13448. So 263 Kelvin equals to static air temperature multiplied by 1.13448. So static air temperature equals to 263 divided by 1.13448. That is 232 Kelvin or -41 degree Celsius. -41 degree Celsius. Now that means ambient temperature, current ambient temperature in the atmosphere is -41 degree Celsius. ISA temperature at at pressure altitude of 30,000 feet is 50 minus 2 into 30, which is equal to 50 minus 60 or -45 degrees Celsius. So ISA deviation is actual temperature minus ISA. So -41 minus of -45. So -41 plus 45. So 45 minus 41 is 4 degree Celsius. So that means ambient temperature or actual outside temperature is warmer than ISA temperature by 4 degrees Celsius. Now density altitude. Density altitude equals to pressure altitude plus 120 into ISA deviation. So pressure altitude is 30,000 plus 120 times ISA deviation, that is 4. So density altitude equals to 30,000 plus 120 into 4 is equal to 480. So density altitude is 30,000 480 feet. Okay, approximately 30,500. So this is your answer. Next, if QNH is 999, what is pressure altitude at an elevation of 25,000 feet? So elevation, let's say they are talking about the elevation of your of an airport. Elevation is always measured from mean sea level. So let's draw a mean sea level. Now the atmospheric pressure at mean sea level is called QNH. Elevation is 25,000. QNH is 999. Okay. Now we have been asked to find out pressure altitude at this elevation. Now pressure altitude is always measured from standard pressure setting 1013. Now look at QNH value. It's 999. So standard pressure setting 1013 pressure level will be below QNH pressure level, because as you go down to the center of the earth, atmospheric pressure increases. So 1013, which is a higher pressure value, will be found below QNH pressure level, that is 999. So standard pressure setting 1013. Now let's find out pressure altitude from this pressure level. So pressure altitude will be measured from standard pressure setting 1013. Now pressure altitude is equal to elevation plus this elevation plus this difference between two pressure levels, which is your height difference, which is your height difference. Now what is the pressure difference between them? Pressure difference is equal to 1013 minus 999, that is 14 millibars. Now we know that 1 millibar equals to approximately 30 feet in height difference, or 27 feet, the accurate value in height difference. So 14 will be equal to 14 into 27, 378. So this is equal to a height difference of 378 feet. So pressure altitude is equal to 25,000 feet elevation plus a height difference of 378. So pressure altitude equals to 25,378 feet. Okay, easy. 7. If pressure altitude is 22,800, elevation is 22,000, what is QNH? So now this particular question is the reverse of the previous question. Okay, so concept remains the same. Let's consider this is your airport. This is your, now pressure altitude is more than elevation. That means QNH is less than standard pressure setting 1013. So let's say this is your QNH. This is your standard pressure setting 1013. Elevation of this airport is 22,000. Pressure altitude of this airport is 22,800, right? So this is 22,800. This is 22,000. So the difference between them is 22,800 minus 22,000. So a height difference of, that is equal to a height difference of 800 feet. A height difference of 800 feet will be equal to a pressure difference of 800 divided by 30, let's say approximately 30, it's 26.6, and 800 divided by 27 is 29.6. So 800 divided by 27, because 1 millibar of pressure difference equals to 27 feet. So that is equal to approximately 30, uh, 30, 30 millibars, approximately 30 millibars. So the standard pressure setting is 1013. So QNH will be less than 1013 by 30 millibars. So QNH value equals to standard pressure setting minus the pressure difference. So 1013 minus 30. So 1013 minus 30 is 983 millibars. 983 millibars. The wind at an airfield is 330 at 30 knots. What will be the wind component along the runway and across the runway? That means we are told to find out headwind component and crosswind component, right? So runway 04. So let's say this is your north datum. So runway 04 will be something like this. 0422. Winds are originating from 330 at 30. 330 at 30 knots, right? So if you are taking off from runway 04, this will serve as a tailwind. If you are taking off from runway 22, it will be you will get a headwind coming from the right hand side. So now they have asked us to find the wind components along runway 04. So a long track component equals to minus standing, which stands for headwind component, into wind speed multiplied by cos theta. Now theta equals to wind direction minus runway in use. So winds are 330, runway in use is 0404, that means 40 degree. So 330 minus 40 is 290 degree. So a long track component equals to minus wind velocity 30 knots into cos of 290. So minus cos 290 is 0.342 something multiplied by 30, that is equal to 10.2 knots something. Okay, so approximately 10 knots. So you are getting an along track component of 10 knots. Next, crosswind component or a cross track component. Okay, crosswind component equals to wind speed into sine theta. So wind speed is what? It is equal to 30 knots sine of 290. Sine 290 into 30 is minus 28. So minus 28, that means the wind's minus stands for the left hand side. So that means the wind is coming from the left hand side at a crosswind. So the crosswind component will be 28 knots. Headwind or correction, tailwind component will be 10 knots. Okay, next. The maximum factorized crosswind in which a particular multi-jet aircraft can take off is 10 knots. So the maximum crosswind limit is 10 knots. What is the acceptable wind? Question mark. Okay. Now, this is your north datum. The runway in use is 0927. So 0927. Winds are coming from 330. Okay. So that means somewhere from here. Now we have to find out this x value, which stands for wind speed. So we are going to use the crosswind formula. Okay. The crosswind formula, which is wind speed into sine theta. Now what is the crosswind limit? 10 knots. 10 knots equals to wind speed into sine theta. What is the value of theta here? Which is wind direction 330 minus runway direction 0990. So 330 minus 290 is 330 minus 90 is 240. Right? So sine of 240. Therefore wind speed will be 10 divided by sine 240, which is equal to 10 divided by minus 0.86. So 10 divided by that is equal to 11.6 or approximately 12 knots. So minus stands for winds coming from the left side. So wind speed is, so therefore therefore the wind speed is, wind velocity is 330 at 12 knots. So this is the value. Next. The reported wind at an airfield is 270 30 knots. What along track and across track wind components must be used in for takeoff if you are taking off from runway 29er? Okay, so again, let's say this is your north datum. Runway 29er will be like this. 29, the reciprocal of which is 290 minus 180, 110. So runway 11 will be here. So we are taking off from runway 29 like this. Winds are coming from 270 at T knots. So theta, wind velocity minus runway. So wind velocity is 270, runway is 290. So that is equal to minus 20. Minus 20. Wind velocity, correction, theta, the value of theta is minus 20. Now, a long track component equals to minus, in case of headwind, wind speed into cos theta. So minus wind speed is 30 knots, cos of minus 20. 30 cos minus 20 is 0.93 into 30 is 28 knots. So you're getting an along track component of 28 knots. A cross track or crosswind component will be wind speed into sine theta. So wind speed is 30 knots into sine of minus 20. So sine minus 20 into 30 is minus 10 knots, implying the winds are coming from the left hand side, right? So this is your answer, minus 28 knots and minus 10 knots. That's it. So this concludes our lecture. I hope you have understood all the answers that I have solved, questions that I have solved in this particular video lecture, the explanations, the conceptual clarity. If you have any doubts, questions, let me know in the comment box of this video. Thank you for your time. Please subscribe to this channel if you haven't yet. Share this video lecture with your friends and hit the like button if you have definitely liked this video lecture. Thank you.